I think we are ready to go. Let me, you can see the screen. Someone say yes, no. So can we momentarily turn our um, video on just to see, since it's our first meeting, I request that. Okay, thank you. Yeah, first off, I mean, I'm requesting you don't have to, okay? Um, uh, Gyanashri, I've already seen your face. Yeah, first, I'd like to thank you for cooperating with me to have online. I am visiting the US partly due to personal reasons, partly due to professional reason, and I will be in and I mean this. So I expect to have it in hybrid mode, the class, until the third week of September. Okay, I'll be in at CMI end of this week for a couple of weeks, and then again I'll be taking off. So when it is online, and so we need to have two times. Okay, one for offline physical classes and online. Maybe we can do it. I mean, we can, I don't know, maybe there'll be more people joining in. At least there were 15 people who seemed interested and they got themselves enrolled. But here I see only 7 people. But nonetheless, we can do that. At least we have to get some kind of an arrangement. Is for the online class, is 6:30 p.m. okay? Is if 6:30 p.m., as I have requested right now, is not okay with some of the people here. I'm assuming some of the people here or a subset of the people will be interested in the course and will be interested in attending at least the first few lectures. Okay, so if it is, say, raise your hand if it is not convenient, 6:30 p.m. Okay, the day of the week we will decide. Okay, but just the time, 6:30 p.m. If I don't hear from you, I'll assume it's okay. Okay. As I said, I will be recording all lectures until it we go fully physical mode. After that, I won't be lecturing. All the lectures till end of September, when I'll be in and out of Chennai. I will be recording, and links to those things I will publish. And all the slides, I mostly I will be using slides, and the slides will be made available. And the links for the slides will be made available as well. Everything will be included in a Google Sheet, and I will publish in a few days the lecture schedule as well. Okay. Um, yeah, now, yes, let me see. So, of the people here, who are the people? Lucky, your MSc second year.
Yes.
Jan, your
I'm also MSc Computer Science second year.
second year. Okay. Himadri,
So same.
Second,
MSc second year.
Siddhant.
I'm BSc 3, sir.
Three. Okay, one BSc three. Okay. Kathakali, I know that you are second year. Saumil, I mean, you're enrolled, but there was no affiliation in your case. You are?
Oh, I'm from MSc second year.
Oh, okay, good. Yanishri, you're
I'm
also
from
second.
MSc second.
MSc first year, huh?
Second year, MSc second year.
Oh, okay. So almost all of yours second year. So that is, yeah, only one person undergraduate. Okay, third year. So I'll ask, I mean, I'm assuming that all of you MSc folks would have had logic course, correct? Yeah. Um, yes. Okay.
Yes,
How about,
we all had logic.
yeah,
Yeah, I think we all have done logic.
you done logic. Okay, including that one person who was, once again, who was is Siddhant, is it? Siddhant,
So
correct?
I'm taking logic now,
Um,
but I've done one logic course, like not the
yeah.
logic course. I've done a
So
logic.
even if you have taken the logic course, say I will be covering doing logic recap. Okay, so because the way that I do logic is slightly different. I mean, it'll be hands-on logic. I want you to. I'll cover how to model. I mean, use logic to model. Certain software and computational systems in a certain way and so on, and all logic concepts, etc. Of course, there's important logic concepts that you need to understand, various things like satisfiability and satisfiability, validity, and those kinds of things. But I want you to actually to be using certain tools. Okay. Hi, Ryan Hota. We were just going through, he's here, I think he's gotten in, or maybe he's still joining. Okay, so I will say hi. So I will have assignment, I mean, initial assignment to actually, I mean, do those things on Z3. It's a SMT solver where you can type in your formulas, check if they're true or not, and so you get the feedback. I whatever logic that I teach, like 2 to 3 lectures I'll be devoting to logic, mostly in using logic to model, encode certain problems, and model software. And logic can be used in lots of different ways to model. Here I'm talking about first order logic. Okay, first order logic. Um, and I'll talk a little bit more. So, although you might have had logic, I do encourage you to attend those lectures and get a flavor for what the things are, and then do the assignment problems that I'll be giving, and I call them as logic exercises using Z3. That is the tool that we'll be using various tools. Z3 is the basic bread and butter logic tool, that is an SMT solver or SAT solver. So I want you to do, once you feel comfortable with using logic for encoding and the thing, and even if you've not taken a logic course, I'll be fine with you taking it. But in your case, you have already taken logic course, but even so, I want you to attempt seriously attempt those and solve those problems. Okay. Yeah. um, yeah, so let me go full screen. So do we have anybody new here? I know Ryan Hotter tried to join, but he's not here. Okay.
Sir, Ryan Hutta asked me to inform you that he's very sick, so he went to doctor or something. That's why he couldn't join.
Okay, okay. Inform him that, ask him to take care and tell him that this is being recorded. Okay. And I will send him an email. That's okay. Yeah.
Okay,
Thank you.
sir.
Okay, right now, I'm the only lecturer. I might have guest lecturers to lecture on special advanced topics later in the course. Right now, I do not have any teaching assistant for the course. I might ask one person that I have in mind to assist me, but right now I'm the lecturer. So, the purpose of today's lecture is to motivate the course, give a flavor of the course content and the syllabus, and also the grading structure that I have in mind. Okay, and that is a thing. And then, of course, to finalize a schedule for the course, both online and offline, once I move back to Chennai. Okay, you can see the screen, I'm assuming. Yeah. I mean, you can see this course is applied logic course. Okay, in a nutshell, that's what it is, and an application of logic to analysis, doing analysis of software systems. Why do we need to do this? Okay, so you see here a train, a complicated integrated circuit and cars. Okay, now we have all these are complex appliances, machines, okay, which use software. I mean, the software is ubiquitous, okay? Not just small software, but software, millions of lines of code that are controlling critical functionalities in their operation. Therefore, any glitch in the software,
Sir,
yes.
sir, sir, are you sharing screen?
Oh, am I not? Oh my God.
Is the screen is shared?
I
No,
think,
sir, nothing.
oh, I'm sorry, Jack. Thank you. Thank you for noting.
Yeah, now it's showing, sir. Yeah, sir, now it's showing.
Okay.
Yeah.
Yeah, now you can, huh? Yeah, I was saying that, okay, software is ubiquitous and it is used to control critical functionality of complex day-to-day appliances and systems that you use take for granted in practice, like cars, nuclear reactors, airplanes, and even in industrial automation, which may not touch our life directly, but indirectly, and even space shuttles and things like that. And these are not simple software; they're very complex software, and any flaw in them can cause, because they're safety critical and mission critical, can cause lives, danger to lives, as well as if they're mission critical, then a loss of life as well as loss of material. So the point is that ensuring assuring their correctness is a very important goal. Okay, I'll first give you a few examples there, of software errors, hardware or software errors leading to very serious issues in real life. Okay. There is a link that I will give you later on in this slide, which kind of compiles a list of software such software glitches that have led to either loss of lives or injuries, and a lot of loss of money for the people that are building these systems. One is this thing called Therac 25. Okay, it's a radiation therapy machine, and it involved in at least six accidents between 1985 and 1987. That seems a long time ago. And there was a software there controlling the level of radiation that it was intended to project, and that there were massive overdoses, 100 times the intended dose, and it caused the death of three patients. And the cause of this was a design error in its control software. Okay, and that was something called race condition. Some of you might have heard of that, and and the race condition is notoriously hard. This is a concurrency error. How do I? Okay, so let me show you, switch to another slide. Okay. So, for example, how many of you, data races usually occur when you have concurrent multi-threaded programs or concurrent programs. For example, here, there are three threads, all of which are trying to access a shared a variable. In this case, x and y. Okay, what is the problem with this thing? Anybody? There are three threads here, and all of them are trying to read and assign to common variables. Okay. So, and this is an instance where you can have data races. What's a data race? Have you heard of a data race? And I'm saying that this is an instance of a concurrent program which has data race. Okay. So a data race is said to occur when the result of executing a concurrent program varies depending upon the schedule that is used. The schedule that is used to schedule these threads. Okay, so you want predictable results when you execute an implementation. I mean, when you have a parallel implementation of a problem, and if these multi-threaded programs are accessing shared variables, then you will have to do it in a synchronized fashion. So in this case, you can see you can work it out, yourself. The eventual value that gets assigned to x and y after all these threads terminate can be different. There are lots of different possible values. Okay, depending upon how what schedule you use to in executing these threads, and usually one doesn't have control over the schedule that is done by the operating system, and that can lead to unpredictable results if you haven't taken care of to synchronize the uh, access to shared resources. And this such ensuring that there are no race conditions is notoriously difficult. Why? How do you normally ensure that there are no race conditions in a multi-threaded program? Anybody? How would you?
Like
Yeah.
mutual exclusion primitives, maybe locks and something.
That is right. Mutual exclusion is a design, is a synchronization primitive that you can use to ensure that that is correct. But my question was about in testing. Okay, normally you test, right? Okay, even with mutual exclusion, you have to ensure that your mutual exclusion is working. Okay, so I mean, I was getting to the point where if you were to test this, you have to test for all possible schedules, and you can see that this the so this is exponential in the number of instructions that you have in each of those threads. And it is exponential, and the exponential factor is the number of threads that you have and the number of instructions. And therefore, if you have to test it to ensure, even with mutual exclusion synchronization primitive, this will be non-trivial. And so testing of concurrent programs is notoriously complex and difficult. And this was the kind of error. So what he was talking about, someone who said mutual exclusion, is you can have something like this before you enter, before you have an access, you try to access a critical resource, a shared resource, you'll have to set something, a synchronization variable called a semaphore. You have to set that one. It'll be like it's like a lock variable. You have to lock the resources and then before you access. Yes, that is one way to do. But even with that, you see, when you interleave these actions to account for all possible ways you can schedule them, the number of execution runs that are possible and the number of states that you will have to explore in your testing strategies grows exponentially, and it becomes very large, and therefore the testing traditional testing methods are very it will be inadequate. Okay, and that was the kind of uh, thing that caused this one. You can see I'm back to the Tarak 25. You can see the screen, right? Yeah. Okay. Yeah, and that was what was yeah, that caused this catastrophe. Okay, and another thing from the space application is this Ariane 5 rocket system. So that crashed. Okay, here there was no loss of life, but it cost more than $500 million of money. And once again, the cause of failure here was a data conversion error. It was a C code, and in C code, the conversion type conversion rules are so complex, and it seemed, that occurred when 64-bit floating point was being converted, and that exact conversion rules, the effect of those conversion rule was not being accounted for, and sometimes overflow and underflow. This can cause overflow and underflow, and that was not fully, the impact of that was not fully analyzed, and that cost the NASA, I think, a lot of money. And more recently, I mean, for me, more recently, and probably not for you, in 2003, once again, there was a major blackout that occurred, bringing the entire grid in the northeast corridor of US, where and caused a big blackout, and that was also due to a glitch whose source was traced to a race condition not being resolved properly in its control software. Okay, and you can go on. Now, this is another kind of error. So where in Toyota, Toyota had to recall lots and lots of vehicles, and here the cause was once again it was caused due to a short delay. This was real time. When you have parallel systems, they are synchronous parallel systems, but they're hard deadlines that your scheduling of actions not only should be correct, but they also have to meet certain hard timing deadlines. In this case, the application was an anti-lock braking system, and therefore the braking action had to happen within a certain hard delay, and that was what was not being met. Okay, and this once again is involves worst case time analysis of multi-threaded parallel system, and that caused major loss for Toyota. Okay, and here is another one, which is from a security application, and this was due to, so this is a open SSL. It's a security layer that is used in Linux boxes, and and you know that Linux boxes are everywhere, implementing going into coffee machines to very complex systems. And what I want to draw your attention to is the cause of this error. There was a buffer overflow error embedded very deep in a layer very close to the kernel of Linux. Okay, and such errors, which are in the boundary of hardware and software, uh, are very difficult to locate and even diagnose. And what some people did, hackers, was to exploit this buffer overflow. By observing the buffer overflow, they were able to get certain critical high security information, which was then used to break the security layer, and resulting in a lot of stolen identity numbers, cards, and and a loss of a lot of money to people and the software vendor. Okay, so these are some examples, and you can go visit this link. And I can also give, and this has some, I don't know if this is an active link. There was also one link where a group of people, a news group, where they were, which is a very active and a lively link, where they keep compiling such horror stories that have that soft glitches in software have resulted. Okay, so what is the point of the takeaway of all of this? What I'm doing? Software verification is very hard. Okay, and there's no exaggeration here. Okay, this one is showing a Superman trying to save. A catastrophe, and it is in terms of complexity and the impact that it can have on life, loss of life, and loss of business can be quite significant. Okay. Um, and therefore, there is a lot of interest in using a method called formal verification or formal methods of using. That is what is the term that is used for applying logic or automata for yeah, what are okay, before I get to that, traditional methods I've already pointed out is simulation and testing. They can only reveal presence of bugs, but they do not guarantee absence of bugs, that you get 100% coverage. This is impractical for the reason that I already pointed out in concurrent systems or even in sequential systems, because the data, the size of the data is so huge that it is physically impossible, impractical to cover all possible scenarios that you actually need to test. Okay, so simulation, because uses dynamic methods to by running the system, it always has this disadvantage that is not able to guarantee absence of bugs. Okay. Second, it is expensive, consumes a lot of resources and time consuming. So the question is, can we have methods that guarantee absence of bugs? And that's what the thrust of this course is. And there are, I mean, there is this compendium of methods that go under the name of formal verification. These methods are based on logic and automata theory. And what is, there are two ways of doing it. Either, post hoc verification, okay, use logic to guarantee 100% coverage, and that is called formal verification. Or you build your system, you construct your system that guarantees correctness, and that is called formal synthesis. Okay. Yeah, so this course primarily does, yeah, so let me first, okay, before I get to the outline of the course. So what is formal verification? So these are methods based on logic and automata theory. What it involves is it develops a way to precisely model software behavior in a suitable logic. Then develop a way to specify the expected behavior, that is the requirements. These are specifications on the way that the software is expected to behave, also in a suitable logic. And of course, automata can also be used here. Automata logic, they are interchangeable. So I use the term logic, but there are automata theoretic methods as well. And then develop a way to prove formally that the software meets the requirements. And here is the key thing: for all possible behaviors under the input constraints. And that is how these methods guarantee 100% coverage. Sometimes these methods are called static analysis or static methods, to contrast it with simulation, which is a dynamic method where you execute the program to check the expected behavior. Whereas here, the assumption is that you not only have a formal model of the software, but also the user is expected to give the requirement in a informal logic, and then you use methods to prove once and for all that the software meets the verification for all possible behaviors. Okay, so as I mentioned, another way is to use synthesis. And what is synthesis? Once again, formal synthesis, are methods that where the program is constructed, and the way it is constructed itself guarantees that it is correct. So here you start from a precise specification of the program in a suitable logic, just like the input for the formal verification as we saw before, and you develop an inference system. What is that? Just a set of rules, like you have rules in logic to prove that two formulas are equivalent or they're valid or satisfiable. And similarly, you can have an inference system that works on refining the specification into a sequence of statements that form a program. And the inference system, the rules of the inference system are set up such that every time that you instantiate and apply a rule from the inference system, that you are preserving the behavior, okay, of the refined system. Okay, so that way, once at every step, you're guaranteeing that what you have, the program that you have, is complies the meets the specification. Okay, so I mean, there have been lots of things. This is certainly more complex, okay, in terms of complexity, complexity, much harder problem than formal verification. And people, so it is not, while formal verification has scaled in practice, and it is being used, maybe not in mainstream, to fully verify, but in certain safety critical and niche application, formal synthesis is not as widely used. But now, okay, one can ask the question, does synthesis even have a relevance in the age of ChatGPT, which can, produce programs automatically, okay? But there is one difference between formal synthesis and the way generative AI constructs program or translates program, and that is ChatGPT does not guarantee correctness. You can get very close to what you want, but still there is no guarantee of correctness. So nowadays, formal synthesis, while earlier it used to be completely based on logic, it raises an interesting question if we can leverage the power of generative AI while complementing that with formal logic to guarantee correctness. There's a lot of work in this area as well. Now, this course will be concentrating on formal verification. And towards the end of the course, I will be covering, as part of advanced topics, a bit of formal synthesis. Regarding using generative AI for this purpose, I don't think I'll be covering it as part of the thing, but what I want you to do is when we have, you'll be doing projects and problems in here. So generative AI can not only be used to assist in formal synthesis, but it can also be used to assist formal verification, because developing the proofs. And while I'll not be covering that aspect in the course in a detailed fashion, as part of assignments and so on, I encourage you on your own initiative to use generative AI as you feel fit, okay, to solve your problem if you wish, okay. And at least for some of the problems, I may ask you to actually use on your, voluntarily on your own. But I won't be covering. Okay, mainly the purpose of this course is to cover logic, the techniques based on logic to address this problem. Okay. Any questions so far? Okay. Okay. So a little bit of history where it all started. Okay. The beginnings of software verification, if you really want to see the earliest reference or attempt to doing it, it goes as back as Turing himself. Okay, so he in the 1950s, there is a paper, and if indeed I can locate it, I will send you a hard copy, or I mean a link to it. Turing talked about this problem of correctness proofs of Turing machines or low-level programs. Okay, he did not develop a complete system, but certainly he formulated that problem and raised this as a challenge for people to consider. The first real attempt at developing a formal system to verify this was done by Floyd in the 60s, in the mid to late 60s, where he proposed an assertional reasoning system that worked on flowcharts of programs to show that they, you start with assumptions, input assumptions, and post assumption when the program terminates what it is supposed to satisfy. And these assertions were written in okay, in certain in logic, and he showed how to actually calculate through some calculus how you could guarantee that the program represented by the flowchart indeed satisfied the specification, the requirement specified by those assertions. Later in the same, Hoare developed a complete inference system, much like you see first order logic. The inference system for first order logic gives the rules of inference. Hoare developed a complete inference system wherein you could prove programs to be correct by applying the rules in his system. Sorry. And Dijkstra, this was still pencil and paper like exercise. There was no automation in Floyd's system as well as Hoare. People were able to apply the rules that they developed to reduce the proof of correctness of the systems into performing calculation in symbolic logic. Where Dijkstra, and here you're moving to the 70s, did was he introduced this notion of weakest precondition and doing certain analysis that led to facilitated automating these doing these calculations. And this led to later, this is a very significant milestone, as it led to people building systems to automate this process of proving correctness of programs. So that's where it started. And among these things, the logic developed by Hoare is still today, and this notion of weakest precondition, they kind of form the basis for almost all techniques and tools that are used in practice. So we will be covering Hoare logic, I'll be introducing Hore logic and the notion of weakest precondition. Okay. Uh, okay. So speaking of, and this is just for a historical thing and where it all started, and now, there are so many techniques and tools that exist, and some of which are used in practice in this scale to even realistic things. So I'll have to, and this picture kind of um, uh, puts all the different techniques, major techniques and tools that exist in a nutshell. It gives a big, perspective on thing. These tools and techniques are can be determined, I mean, can be categorized based on these parameters, how scalable they are in the sense, how scalable in practice, I mean, measured in terms of lines of code and the kinds of systems that they are able to deal with, how automated they are. I mean, are they push button or does it require a lot of human interaction? And how complete they are. By what do I mean by completeness? Are they able to prove all what are the kinds of properties that they can actually prove, and what are the kinds of systems that they can actually the system means programs that they can actually prove. So based on these things, so there are one can broadly categorize various verification technique approaches. One is static analysis, sorry, static techniques called static analysis. These techniques are very scalable in the sense they can be used to analyze programs that are millions of lines of code because they're fully automated, but they're not complete. They're not complete in the following sense, okay? In two sense. One is the kind of properties that they can prove are limited, okay? And I will get to that in the next slide. And also, they don't give a precise answer, much like compilers when they say, there's a type error or or a bounds error. They're like warnings. Here it trades precision to for completeness. Okay, and therefore they're not complete. They could be they when they say there is an error, it means that there is a potential error. But after their analysis, if they say there's no error, then of course they guarantee that there are no errors. The model checking is it's also another technique that is automated and it is very precise, at least for the kinds of properties that they can verify. They may not be fully complete, but yes, they are fully automated. But model checking is not a fully complete, but for those properties that they're able to solve and for the kinds of systems that are applicable, they are push button. Then there are other whole compendium of techniques that fall under interactive theorem proving. Here they are they are not as scalable at all. They are not as scalable, and some systems, but they guarantee completeness both in terms of the kinds of programs that you can apply to and the kinds of properties that you can apply to, because here these one class of systems, they are actually allow you to model your program in a very expressive logic, and the same logic can be used to specify your properties. And but the catch here is that they are not automated. Okay, and it requires human interaction in order to develop the proofs, and for that reason they are not as scalable as some of these techniques. Okay, so what we will be doing, okay, so any questions here? Okay, so as we move in the course, you will hear more and more about this. This is just to give an overview. So we will be um, the course will we will be covering some techniques and tools from each of these three methods, more so from static analysis and model checking, less so in interactive theorem proving. But there is a style of interactive theorem proving that which is quite automated, maybe not as automated as model checking and static analysis, that I will be covering in the course. Okay, let me see what is the time. So yeah, so we still have some time. Okay, so what does static analysis mean? Okay, static analysis, it has roots in compiler construction. Okay, uh, you can view these techniques as extending compilers to deal with more semantic information, analyzing and then concluding, deriving semantic information about programs. For example, rather than just checking syntactic correctness and simple type correctness, you could imagine that you can these techniques can start analyzing array out of bounds, null pointer dereferencing, overflow, underflow, and even more sophisticated things, and analyzing them and giving answers to them more precisely than what a simple compiler can do. Okay, so and these, as I told you, don't always give you precise answer. But when they say that there are no errors, they do guarantee that there are no errors. But when it says there is an error, it should be viewed as that a warning that there could be errors. So there are more further analysis that is required. There are lots of commercial tools in this space that are available and that are used in practice, but they're all very expensive tools to get license for. But what we will be using in the course for you to get a hands-on experience will be a tool called Pharmacy. This is an open source tool. Okay. And there are other versions of these tools that can perform worst case execution time for real-time systems in avionics and automotive things and so on. And all these things are based on the same techniques which come under static analysis. And we'll be covering both the theoretical foundation of static analysis as well as letting you lay your hands on through pharmacy to actually apply it to some real software. Okay. Oh, let me skip this guy. Okay. So what is model checking? You check semantic properties. Once again, this checks semantics property about programs. But the way it does is it searches for the property violations and produces a counterexample. And this search is technically exhaustive. It's very much like developing a proof, but the proof is being constructed automatically using algorithmic methods. And how it is able to do this is without the complexity blowing up is by it restricts to certain specialized logic called propositional temporal logics, to express the property that you want to verify R. Okay, so in this domain and there is a version. Yeah, so we'll be looking at three different tools: new SMV, Euclid Phi, and something called CBMC, which works directly on C programs, and it does a restricted form of version of model checking, where it allows you to analyze, guarantee that are, bounded analysis of your programs. Okay. Now, okay, here's the where the tools that we study and the thing. For each of these things, model checking, static analysis, and the kind of interactive theorem proving that we will be um, doing. We will be covering both. Not before we cover the tools, we will spend the theory behind those tools, the techniques that go into building those tools, and then the course will give you an opportunity to use those tools. But I don't have a slide for interactive theorem proving. I mentioned a little bit about interactive theorem proving. What is the kind of interactive theorem? See, interactive theorem provers are of two kinds. One is it is it is primarily built. I don't know how many of you have heard or used. Maybe you guys, I don't know if you've had an opportunity to take proofs and types, the course proofs and types. And it's been a long time. I with Suresh used to offer a course on interactive theorem proving. How many of you know what an interactive theorem proving is? If there's anyone who knows what a theorem prover is,
A little idea, Professor, I have, but not like a good
who's
one.
who's this?
Ayan.
Ayan. Okay, okay. Yeah, okay. So let me see. See, theorem provers are tools that mechanize to construct proofs in a particular logic. Okay. There are lots of different kinds of provers. Each of them allows a user to construct proofs in a particular logic. For example, there is, there is a tool called COQ, COQ, which does, I mean, I say mechanize and I use the term in a very measured fashion. They don't construct, they are meant to, for a human being to use these, and it provides a whole bunch of methods, whole bunch of repertoire of actions that one can use, and they usually correspond to applying a particular rule. And a human being can then use his or her knowledge about how to build proofs in that logic to construct a proof using these commands. I mean, these commands that the tool provides, such that once you construct, when you use a sequence of commands, they all guarantee that you're applying the inference rules of that logic in a sound way. Okay. So how exactly you apply those commands to successfully construct a proof, that is where the challenge is, and that is where the human input comes into play. Now, those kinds of I call them as classic theorem provers, are very, I mean, they are very hard to use, and the constructing proofs for theorems that are quite sophisticated theorems are very hard. One can use those kinds of theorems to do program proofs as well if you're able to embed the semantics of programs inside those in those logic. That is one way one can do. That is what a complete method using those tools would be. But since they require a lot of human inputs and they cannot be expected to be used by a typical software engineer, what some people have done is they have made this a bit more friendly to use, okay, by uh, uh, not exposing the complexity of the logic that is being used by and that they are embedding under the hood, and also tailoring these things, tailoring these application of constructing these proofs to programming systems. Okay, and by restricting the kind of the way that you construct your proofs. For example, induction is a very powerful method of constructing proofs. It turns out that induction alone is enough, okay, with a few other principles of logic, is enough to construct to verify any program that you in our programming system that you want to verify. Then you provide a lot of automation in that, in using these solvers, okay, like SAT solvers and SMT solvers. And that's what the system called Euclid 5, does. Okay, so Euclid 5 could be used in a mode of using model checking, or it also supports certain theorem proving like um, what did I do? Yeah. So so we use Euclid 5 to give you an exposure to do inductive, inductive developing using inductive methods for constructing correctness proofs for programs. So it's not as difficult to use as a classical theorem prover, but it can prove more things than, for example, static analysis tools or model checking tools can do. So that is the, kind of the, in terms of tool coverage, and this is what I intend to cover in the course. I'm going to skip these two slides. Okay. So I'm coming to the end of the lecture. So what is the course focus? As I've already probably repeated, just to summarize, we focus on verification techniques that provide a rigorous guarantee of quality. I'm using quality here because the quality could be correctness, or it could be other performance measures, okay, are mostly highly automated. So in that sense, the course will not be covering classical theorem provers, but only that are automated to a certain extent. And it'll be focusing on those techniques that have impacted that have had impact in practice, okay, that are being used, these techniques, if not the tools that you get exposed to, at least the techniques behind that go into building go into these tools are being used in practice. Okay, so here's this syllabus. The next 2 to 3 lectures, I'll be doing logic recap with introduction to Z3. So with the intention of, so you'll get hands-on experience of using Z3, and then checking things that you had. Okay. Then I start with background, how exactly, mainly, how you model, how you can use logic, what it means to use logic to model both the behavior of software as well as the specification of software. Then I introduce whole logic, because that is something that is, the concepts of whole logic are pervasive in all of these techniques and so on, in techniques. And then I start with bounded model checking. I may not, the exact order in which I go may not exactly be like this, but there is first this restricted version of general model checking, temporal logic model checking, which is bounded model checking, do static analysis, and inductive model checking techniques, and that's where Euclid 5 comes. Then finally, the modeling of software, we will be covering both sequential software as well as concurrent. And the model checking in its full generality, which I call as the temporal logic model checking, will also be covered. And each of those things, after I cover, I'll be into you will get exposure to the tools, and there'll be problems that you will be solving on using those tools. Okay. Now, the advanced topics are, as I mentioned, program synthesis. Depending upon my mood and what the interest is, I'll be covering maybe one or two of these topics. Um, yeah. I've already spoken about prerequisites. It seems like most of you have had logic, so there should not be an issue. But if you have not had logic, at least I require you to have gotten exposure to be good at discrete math, sets, relations, partial orders, and these kinds of things you should be familiar with or be able to pick up quickly. At the if you sit through, if you don't have logic course, if you sit through my logic recap and then do the initial assignments, and then you're without any difficulty, then that's an indication that you have enough logic background for your thing. But if you go through the course, but if you do have a logic course and also have exposed to theory of computation and programming language semantics, that would certainly be helpful. Okay, here is the grading. I intend to have assignments, at least 3 assignments, some quizzes, and this can happen anytime during the course. But the biggest thing is a small but significant hands-on verification exercises using the tools covered in the course. And you see, I attach a lot of weightage for that. Now, what I'm planning to do in this course, okay, I've not made a decision on that. I want to do do a verification of a distributed protocol, a simple distributed protocol. And I will introduce that problem right at the beginning. So you can start the thinking. It'll be like a running exercise, running problem that you will see throughout the course. So some part of that you will be using for developing a model and so on. So there's a class of protocols called consensus protocols. They are distributed protocols that are used for building infrastructure of blockchain systems. And there is a very simple version of that protocol called a raft protocol, and that's what I'm planning to use. And the exercise will be for you to develop a model of that in one of these tools, and mostly I'll be using Euclid 5 for the project. Um, and be doing that. But you will hear more about that. But nonetheless, I might change that. I mean, that's the thought that I'm having right now. But there will be significant, it may not be all one, maybe be 2 small ones and one big one. That will account for 40% of the work in the thing. So learning outcomes, sources of complexity. See, because these verification techniques very much depend on the complexity of programming languages. Okay, you'll get an in-depth knowledge of program analysis and techniques, and an exposure to current research challenges in this area. Okay, so that's where I want to stop. I have a few slides where you could use CBMC, but since I have not provided any information, I will get to that in the next class. Okay, so I want to end here and take any questions that you might have. I mean, for people who came in late, before there is a logistics thing, so until September end, we will be doing in hybrid mode. Okay. So I want a time to when six, okay, at least for this week, it will be online. Okay, I might have one more class on logic recap. So 6:30 p.m. The next class could be Wednesday. I will announce, okay, but it's 6:30 p.m. like we did today, a good time for all of you to be able to attend as a in when it is in online mode. Okay. Okay. So some chat.
Sir,
Yeah.
is Thursday fine instead of Wednesday?
Yeah. Well, Lucky said why can be 20 or 21. I don't know. I don't know. I didn't understand that. Huh? Lucky,
Yes, sir.
your comment on it says why can be 20 or 20.
Sir, it's the concurrent programming question, the first one.
Oh, sorry, I never.
So,
No, no, no. I will leave it to you as an exercise. You see, you have to look at all possible interleavings. Okay. So, and work it as an exercise. I think there are more than that. Yeah, yeah, yeah.
yeah.
You're right. Why can't be 20? Actually, there are more possibilities than these two things. Okay. Because both X and Y are shared, and then I think they're being manipulated. You can work out all possible interleavings, for the schedule, and there can be more possible data races. Okay, Dhruv Patel says join late. Okay, good. Yeah, since none of you has objected, let me. I want to see what my schedule is. I will. Yeah. So Tuesday, Thursday. Shall we try to have classes on Tuesday, Thursday? This week I might have it only on Thursday. Okay. What day is Thursday? Today is 11th, 12th, 13th. 14th. Okay. So I think Thursday should be fine. The next class will be online on Thursday. Okay. And let's agree to have it on Tuesday, Thursday. On Tuesday, Thursday, for physical class, I will send you an email, or we can have Monday, Wednesday, okay, or Tuesday, Thursday. So I don't know if we could decide here when we next class Thursday online meeting. So let's agree next class to be Thursday online, the same time, 6:30. So people that are seriously interested based on what you have seen so far in the introduction thing, I'll assume that you guys will show up. And so we'll make a decision on the day and time for regular classes, both physical as well as online. Okay, we'll do that. But the next class will be on Thursday at 6:30, and the topic will be logic recap. Okay, thank you. Unless you have any questions. Okay.